the effect of myelination. So on the exam yesterday was a question about whether myelinated neurons carried the current faster than unmyelinated. The original question, which I changed, since we hadn't talked about this yet, was the diameter of the neuron. So certainly a myelinated neuron is going to allow the transmission of the current at a faster rate. And that's because the ion channels that have to open are found along the membrane only at the nodes, and the current flows much more rapidly straight down without having to regenerate itself all the way along. Now, if we didn't have that myelin sheath, all right, can we just have no voltage-gated channels there and just let the current flow straight down without having to regenerate itself and be done with it? And just have the voltage-gated channels at patches? What happens when we don't have the myelin sheath and we only had voltage-gated channels here and voltage-gated channels here? We'd still have the leaky channels, and we'd still have the sodium-potassium pumps, and so our current would get weaker as it moved down. Okay? So in this case, it doesn't get weaker. And it's still of a force strong enough to open those voltage-gated channels. However, it's not so far away that these are not in their relative refractory. So these would still be in a relative refractory period. So when the current goes that direction, it can't open them. Okay? So we maintain our directional flow. Now, somebody this morning asked, well, are the voltage-gated channels still there? They're just covered up with the myelin sheath. In some cases, they may be, but we have diseases such as MS, where that myelin sheath is lost, and the current is not transmitted. So that the voltage-gated channels are not there, and the current is too weak to continue going from patch to patch, where we do have the voltage-gated channels. So they probably were there before the myelination of the neuron, and then were removed in the metabolism of the neuron because they were no longer being useful. All right. So when we look at this, then the diameter of a neuron increases the rate of conduction, and it's a little easier to understand when you talk about water than if you talk about ions. If you have a small diameter tube and water's flowing through the tube, turbulence is created as water molecules bump along the side of the tube, and that creates an internal turbulence. A larger tube, you have ions, the water rather, flowing through the middle, not contacting the surface, and therefore it flows much faster in the middle of the tube, and more of the water in the tube conduit is flowing at a faster rate. That's not quite the way it is with ions. It's more the ion channels that are present than the turbulence. But a larger diameter neuron versus a smaller diameter neuron, even without myelin, is going to conduct faster. Okay? Once we add myelin, it's going to conduct even faster. So where it changes, I don't know what the diameter has to be for a large diameter unmyelinated to match a smaller diameter myelinated, because obviously you're going to have a continuum of that. But for this continuum, a large diameter myelinated is the fastest conducting. And we have them carrying voluntary motor. All right? Involuntary motor, going to your stomach, going to your blood vessels, is the smallest diameter, and they're unmyelinated. So that's the slowest. And then our sensory impulses are in between. Light and touch, pain. I guess itching isn't very important because that travels pretty slowly. Our body doesn't need to respond to that as much, or as quickly, it seems. All right, so on Tuesday, we followed now the action potential down to the axon terminal, and we're going to follow that action potential into the axon terminal and talk about how the synaptic vesicles are triggered to fuse. And then what I was working on during your exam yesterday was I took some of the concepts of the neurotransmitters and their receptors from the autonomic nervous system and moved them into neurophysiology. So Tuesday, we're supposed to actually start autonomic nervous system, and we're going to finish neurophysiology, because we're going to cover some of those concepts that I normally used to cover in autonomic. And we'll talk about the synaptic impulse and neurotransmitters and their receptors, and then we'll move into autonomic on Thursday. Okay? So the lab activity from PhysioX that was due on Tuesday is no longer due on Tuesday. I'll make it Thursday, but I would go ahead and start it. The lab itself should be on D2L, but I'll double check this afternoon. I put it up there this summer, so I don't remember. But it should, there is a lab up there, and it should be the current one, but I will double check. So you can go in there and start working on it rather than waiting until Tuesday and trying to get it done between Tuesday and Thursday. But we haven't talked about everything that's on there. Okay? So I would go ahead and get started and do some of it and then finish it up after Tuesday. So there is no work due Tuesday as far as that is concerned.
But everything that was for the quiz on Sunday?
I'll double check on it. It should, so we've covered action potentials. I'll double check and see if I may need to eliminate synapses from the random choices. But I'll leave